In a previous lesson, we looked at spontaneity, whether reactions will occur on their own without outside influence. What we're going to look at today are reactions where the reaction may not actually occur even though it's spontaneous. We want to look at endothermic and exothermic reactions and how a catalyst fits into all this. So just because a reaction is spontaneous, the delta G in the Gibbs equation is negative, meaning it's spontaneous. It doesn't mean it actually will happen. And that's because of some other things that are going on in a chemical reaction. Now, I want to first explore what's happening with an exothermic reaction. What does exothermic mean? It's releasing energy. Okay? So we're going to create a reaction energy diagram. For an exothermic reaction. If it's an exothermic reaction, what's happening to the heat in the system, or the energy in the system?
Oh, it's going down.
It's going down. So it has to start higher than it ends. I just emailed to you, and okay. So it has to start higher than it ends. Okay? So we're looking at energy here. This is energy on this axis. Actually, the energy we're looking at here is the energy that's stored in the system, the enthalpy energy. Okay? And what we're looking at down here is the progress of the reaction. So we just looked at methane, or actually we looked at ethane last. We did look at methane right before that. If we have a chemical reaction that's progressing going in this direction, okay, we could, if we wanted to, since we know that methane's combustion is an exothermic reaction, we could just write the reactants here. Now this is an example. It isn't the only equation you could put down here. You could put any exothermic reaction you wanted to. But it's an example reaction we could put down here because this is an exothermic reaction and we progress from left to right, reactants to products. Okay? The difference between the amount of energy that's right here, that's the amount of energy that is stored in these chemicals. We usually think about that being stored in the bonds. Okay? The energy stored in these bonds is greater than the energy stored in these bonds. So as we go from left side to right side, as the reaction goes from the methane and the oxygen, and when we burn it, we get this stuff, there's less energy in the system. It drops. The difference between the starting amount of energy and the ending amount of energy is the delta H. That's the change in enthalpy in the system. And as the reaction progresses, the system is losing energy. So what sign will the delta H be? Negative. So negative delta H because it's going down. Okay? Now it'd be really nice if that was a slide and we had a straight line going from there to there, but that's not what happens. What actually happens is you have to do something to make this happen. You have to have an activation energy hill. Okay, think about it. Does methane in oxygen automatically burn? What do you have to do to get it to burn? Okay, so you have to have a spark of some kind. Yes? So you have to do something to get it started. And that energy you're adding to the system when you light a match or you give it a spark, that's called the activation energy. Okay? All reactions require activation energy. You may not see it, it may not be obvious, but all reactions require activation energy. Things like the reaction between baking soda and vinegar, for example. You just put the baking soda in the vinegar, it happens, right? But the activation energy is coming from the ambient temperature, the surroundings, the movement of molecules that is already there. Now, not all reactions have enough activation energy supplied by the surroundings or by the environment. Sometimes you have to add activation energy like this. And there are some reactions that have such a high activation energy that it doesn't happen at all. Some reactions that are spontaneous and exothermic don't happen at all because the activation energy is so high. And a good example is the decomposition of diamonds. The decomposition of diamonds is thermodynamically favored. It's spontaneous. Diamonds spontaneously decompose, but they don't really decompose because the activation energy is so high, it's off the chart. So you don't have enough energy to get it started. So let's look at a reaction energy diagram for an endothermic reaction. Okay, so we have an equation for a reaction. The equations just describe reaction. You have a reaction that's starting over here. You have reactants on this side, products on this side, and since it's endothermic, that means that energy is being taken in into the system. So that means that the energy, the enthalpy, that's the energy in the system, is going to be lower in the beginning and higher at the end. Okay? But just like with the exothermic reaction, you have to have some activation energy. There's no chemical reaction that doesn't need activation energy to start. There are some reactions that just sort of seem to happen on their own, but those even get extra energy, that activation energy from the movement of molecules in the environment. So just the fact that the temperature is above absolute zero is enough to make reactions move forward sometimes. So we have to go up this energy hill in order to get enough activation energy to start the reaction, and then we can end up at the end with the products having less energy than the reactants. Now in this case, our change in enthalpy, the enthalpy being the stored energy, so we're looking at energy here. This subscript H just means we're looking at enthalpy energy, energy stored in the system. That would be, in this case, stored in the chemical reactions and products. The change in enthalpy here is, in this case, going down. That's delta H. Okay? I'm sorry, it's going up. And so because it's going up, the change in enthalpy is going to be positive here. Now in this case, the activation energy doesn't go from this hill, this plateau here. It goes all the way from the beginning. Activation energy goes from whatever the starting amount of energy is stored in the system to the top of that energy, the amount of energy that's required to, or you are required to add to the system to make this reaction move forward. That's the activation energy. All right, now let's take a look at how catalysts affect all this. So I'm going to use an exothermic reaction. Doesn't really matter. You could do it with endothermic reactions. Exothermic reaction with a catalyst. So remember, our exothermic reaction, the stored energy in the system is higher in the beginning, lower in the end, and the result is that energy is being given away. This is the energy in the system, so there's more energy at the beginning, less energy at the end. Energy cannot be created or destroyed. It can only be moved around, so we're moving energy from the system, which is what this graph is showing, or this diagram is showing, moving from this to the surroundings. And so we have an activation energy hill. Okay? And we've got enthalpy. All right, the change in enthalpy here, remember, is negative because we were losing energy in the system. There's more energy in the beginning, less in the ending. So there's energy being transferred from this system to whatever the surroundings are. And this is the activation energy here from whatever the starting amount of energy stored in the system is to the amount of energy needed to be added to the system to get everything going, to get the reaction started. What catalysts do, and catalysts are often thought of in a way that's not as accurate as we'd like to be when we're in chemistry. A catalyst is a chemical or some substance that you add to a chemical reaction or in the environment where the reaction is happening that's not used up in the reaction. So you get this catalyst out again when you're finished. You can reuse it most of the time. Sometimes it's slightly different and you can't use it, but you should be able to reuse it most of the time. But what it does is it lowers the activation energy hill. So if we have a chemical reaction where the activation energy hill is so high that the reaction becomes so slow that it's not practicable, then adding a catalyst will lower the activation energy hill. It makes it easier for the chemicals to get started and change from reactants to products, and it has the effect of speeding up a reaction. It doesn't really speed up a reaction. What it really does is lower the amount of activation energy needed to make the reaction move forward. And so this is the effect of adding a catalyst to the reaction environment. Okay, that's what that is right there. All right, so you need to know that a catalyst has the effect of, most of the time, of speeding up a reaction. It doesn't always, but it does lower the activation energy hill. It means that the reaction can move forward with less added energy being put into the system to make it happen, to make it move forward.